Picture this: a single thread in the cosmic tapestry, so vast it defies comprehension, a realm where galaxies swirl like dust motes in a sunbeam. We're not just talking about a handful of stars or even a lone galaxy. This is the Virgo Supercluster, a sprawling empire of light and mystery, home to thousands of galaxies, each with billions of stars, planets, and secrets waiting to be uncovered. Yet, despite its staggering scale, what truly captivates astronomers and dreamers alike aren't the things we can see. It's the enigmas that linger in the shadows, the phenomena so baffling they challenge everything we think we know about the universe. What if I told you that right now, as you watch this, there are forces at work in this supercluster, whispers of dark matter, galaxies moving in impossible ways, signals from the void that science can't explain? Some of these mysteries are so profound they've kept researchers awake for decades, chasing answers that always seem just out of reach, and that's what makes this journey so thrilling. Because the Virgo Supercluster isn't just a backdrop for these puzzles, it's the stage for some of the greatest cosmic detective stories ever told. So let's embark on this adventure together. Over the next 25 stops, we'll dive into the heart of these unexplained phenomena, from ghostly radio waves echoing across millions of light years to galaxies that defy the laws of physics. Some of these enigmas might hint at entirely new dimensions of reality. Others could rewrite the story of how our universe was born. But one thing's for certain: by the time we're done, you'll never look at the night sky the same way again. The Virgo Supercluster isn't just a corner of the cosmos. It's a reminder that the universe is far stranger, far more wondrous than we ever dared to imagine. Ready to uncover its secrets? Let's begin. Deep within the Virgo Supercluster, astronomers face a cosmic accounting error so large it threatens to rewrite the rules of the universe. Imagine tallying every grain of sand on a beach, only to realize half of them have vanished without a trace. That's essentially what's happening here, except instead of sand, scientists are searching for baryons, the building blocks of stars, planets, and even our own bodies. According to every reliable model of the universe, there should be roughly twice as much normal matter here as we've actually detected. Where did it all go? For decades, researchers assumed this missing matter was simply hiding in plain sight, perhaps woven into vast filaments of warm gas too faint to spot. But when they trained X-ray telescopes on the supercluster, hoping to catch whispers of this elusive material, the results were baffling. While some of the baryons were indeed floating in these diffuse cosmic threads, they accounted for only a fraction of what's unaccounted for. The rest nowhere to be found. This isn't just a minor discrepancy, it's a gaping hole in our understanding of how matter organizes itself across the universe. If baryons can vanish on this scale, what else might we be getting wrong about the cosmos? Some theories suggest the missing matter could be locked inside rogue black holes or drifting between galaxies in forms we haven't yet imagined. Others propose even wilder ideas, like hidden dimensions siphoning away particles right under our noses. What makes this mystery so urgent is its ripple effect. Baryonic matter isn't just filler, it's the raw material for everything we see. Its distribution shapes galaxies, fuels star formation, and ultimately determines the fate of cosmic structures. Without solving this puzzle, we're like cartographers trying to map a continent with half the landmarks erased. The Virgo Supercluster, with its glaring absence of ordinary matter, isn't just hiding secrets, it's holding up a mirror to how much we still don't understand. Somewhere in the depths of the Virgo Supercluster, an invisible behemoth is tugging at our galaxy with a force we can't ignore. The Milky Way, along with hundreds of other galaxies, isn't drifting aimlessly. It's racing towards something unseen at over 2 million kilometers per hour. Astronomers call this cosmic siren the Great Attractor, but what exactly it is remains one of the most perplexing puzzles in modern astronomy, the strangest part. When scientists first traced the trajectory of our galaxy's movement, They expected to find a titanic cluster of visible matter, a supermassive collection of galaxies, or perhaps an unimaginably large black hole. Instead, their telescopes revealed nothing. The Great Attractor lies hidden behind the zone of avoidance, a region of space obscured by the dense stars and dust of our own Milky Way's disk. It's like trying to spot a lighthouse through a thunderstorm. We can sense its pull but can't glimpse its light. What could possibly wield such gravitational influence without revealing itself? One leading theory points to dark matter, the universe's most elusive ingredient, clumped together in concentrations so dense they bend the fabric of space itself. Another possibility, an enormous supercluster of galaxies, far more massive than anything we've catalogued, lurking just beyond our line of sight. Some researchers even speculate about exotic structures, cosmic strings, or dimensional folds, creating gravitational anomalies unlike anything in our current models. But here's where it gets even more intriguing. Recent observations suggest the Great Attractor might not be the final destination. There's evidence of something even larger, a mysterious structure dubbed the Shapley Attractor, pulling both us and the Great Attractor itself toward an unknown point deeper in the cosmos. It's as if we've discovered a river's current only to realize it feeds into a vast, uncharted ocean. This isn't just academic curiosity. Understanding these hidden forces could reshape our cosmic address. Right now, we map the universe based on what we can see, but the Great Attractor proves the most influential landmarks might be the ones we can't. Every galaxy in our corner of the supercluster is caught in this invisible tide, swept toward a destiny we're only beginning to fathom. The Virgo Supercluster doesn't just house mysteries, it's actively rewriting the story of our place within it. Amid the bustling cities of stars that make up the Virgo Supercluster, there are ghost galaxies so faint, so ethereal, they blur the line between existence and emptiness. These are ultra-diffuse galaxies, or UDG, cosmic paradoxes that challenge everything we thought we knew about how galaxies form. Imagine a galaxy as vast as the Milky Way, but with only 1% of its stars. That's Dragonfly 44, one of the most enigmatic residents of Virgo. Its stars are spread so thin that if you stood on a planet in its midst, the night sky would appear nearly black, punctuated by just a handful of distant suns. Yet despite their ghostly appearances, these galaxies aren't fragile. In fact, they might be among the most massive structures in the universe. How is that possible? The answer lies in what we can't see. Measurements of Dragonfly 44's gravity reveal a shocking truth. This wispy galaxy is weighed down by an enormous halo of dark matter, a hidden scaffold so dense it defies explanation. According to the numbers, dark matter makes up over 99% of its mass. That's like discovering a balloon that looks light as air but somehow weighs as much as a mountain. So how did these cosmic wraiths come to be? Scientists are locked in a heated debate. One camp argues UDGs are failed galaxies, places where normal matter never quite pooled together enough to ignite star formation on a grand scale, leaving them stuck in a perpetual state of dim adolescence. Others propose a far more violent origin, that these galaxies were once normal, vibrant systems until gravitational encounters with neighboring galaxies ripped away their stars, leaving behind only their dark matter skeletons. But here's where it gets even stranger. Some ultra-diffuse galaxies in Virgo don't fit either narrative. They're not just faint, they're pristine, untouched by the collisions that typically sculpt galaxies. This raises a tantalizing possibility. Could UDGs be relics from the early universe, frozen in time? If so, studying them might be our closest window into the conditions of the cosmos billions of years ago. Every new observation deepens the mystery. Some UDGs host globular clusters, dense knots of stars, in numbers that rival much brighter galaxies. Others drift through space completely isolated, as if they were never meant to be part of the cosmic web at all. What's clear is that these ghostly giants are rewriting the rules. They prove that a galaxy's importance isn't measured by its glow, but by the secrets it guards. And in the Virgo Supercluster, the faintest whispers might be telling the loudest story. Hidden beneath the visible tapestry of the Virgo Supercluster lies a skeletal framework so vast it binds galaxies together like beads on an invisible string. These are dark matter filaments, threads of the universe's most mysterious substance, stretching millions of light years across the cosmic void. Unlike the galaxies they connect, these filaments don't emit light, absorb it, or interact with ordinary matter in any way we can directly observe. Yet their gravitational fingerprints are everywhere, warping the fabric of space itself. One of the most compelling clues to their existence comes from an effect called gravitational lensing. When light from distant galaxies passes near these invisible strands, it bends, as if traveling through a gargantuan magnifying glass. Astronomers can map these distortions, tracing the outline of something massive yet utterly unseen. The resulting images reveal a cosmic web far more intricate than anyone predicted, with filaments crisscrossing the supercluster in a pattern that mirrors the neural networks of a brain. But the plot thickens. While we've glimpsed these filaments indirectly, their true structure defies expectations. Some appear wispy and tenuous, while others seem dense enough to rival entire galaxy clusters in mass. Even stranger, their distribution doesn't always align with the visible matter around them. In some regions, galaxies march in lockstep along these dark highways. Elsewhere, filaments stretch into voids, pulling at nothing, as if the universe left blueprints for bridges that were never built. What could explain these discrepancies? Computer simulations suggest dark matter should form a relatively uniform web, with filaments growing thicker at the intersections where galaxies cluster. Yet reality paints a messier picture. Some filaments fork abruptly like fractured tree branches. Others vanish into regions where no known physics predicts they should exist. It's as if we're seeing only shadows of a deeper structure, one that might involve unknown forces or even interactions between dark matter and other hidden elements of the cosmos. Perhaps the most tantalizing possibility is that these filaments aren't just dormant scaffolding. There's emerging evidence they might actively funnel gas across the supercluster, feeding star formation in distant galaxies like cosmic umbilical cords. If true, dark matter wouldn't just shape the universe, it would sustain it. Every new observation peels back another layer of mystery. Are these filaments stable over billions of years, or do they shift and dissolve like smoke? Do they harbor rogue black holes or other exotic objects we've yet to detect? One thing's certain, the Virgo Supercluster's hidden architecture is far more dynamic and far stranger than we ever imagined. At the heart of the Virgo Supercluster, a cosmic gun fires particles across space at nearly the speed of light. This is the M87 jet, a supersonic beam of plasma stretching 5,000 light-years from its source, the supermassive black hole at the galaxy's core. But here's what baffles scientists. The particles in this jet don't just move fast, they reach energies that smash through theoretical ceilings, accelerating to levels no known process should allow. Picture a river flowing downstream, except instead of water, it's a current of electrons and protons moving so fast they glow with the energy of a trillion suns. According to conventional physics, magnetic fields around black holes should act like cosmic speed limits, capping how fast these particles can travel. Yet the M87 jet laughs at these rules. Observations from radio telescopes to the Event Horizon Telescope reveal particles in the jet's inner regions accelerating to over 99% light speed, then somehow gaining even more energy as they stream outward. It's as if a race car kept finding new gears long after its engine should have burned out. So what's powering this impossible acceleration? One leading theory points to shock waves rippling through the jet, cosmic sonic booms that transfer energy to particles like a series of interstellar catapults. Others suggest tangled magnetic fields near the black hole's event horizon act like particle slingshots, flinging matter outward with incomprehensible force. But neither explanation fully accounts for the jet's most extreme energies. There's growing evidence that something far stranger is at play, perhaps gaps in our understanding of plasma physics, or even exotic quantum effects emerging in the jet's ultra-rarefied environment. The mystery deepens when we examine the jet's structure. Unlike the smooth, focused beams predicted by simulations, the M87 jet kinks and twists like a writhing serpent. Bright knots of material appear and vanish along its length, suggesting pockets of runaway acceleration that come and go. Some researchers speculate these features hint at a hidden dynamo near the black hole, a natural particle accelerator far more efficient than anything we've built on Earth. But the real revelation came when scientists compared the jet's behavior across different wavelengths. X-ray observations show particles emitting light in ways that defy standard magnetic field models. Instead of the orderly spiral paths predicted by theory, the particles seem to ricochet chaotically like pinballs in a cosmic arcade. This turbulence might hold the key to their extreme speeds, a phenomenon called stochastic acceleration, where random collisions add energy unpredictably over time. What makes the M87 jet so critical isn't just its defiance of physics. It's a laboratory for the universe's most extreme conditions. If we can decode how nature builds such powerful accelerators, we might unlock secrets about black holes, dark matter, and even the origins of cosmic rays that bombard our planet. Every flicker in this celestial beam carries clues, whispering of forces we've yet to name and energies we've yet to harness. The Virgo Supercluster doesn't just host mysteries, it's showing us where the boundaries of physics truly lie. In the Virgo Supercluster, some galaxies aren't just old, they're cosmic fossils frozen in time. These are the red and dead galaxies, massive collections of stars that burned bright in the universe's youth but mysteriously shut down their star-forming factories billions of years ago. Today, they glow a dull red, packed with aging stars and devoid of the blue sparkle of newborn suns. What could possibly halt star formation on such a colossal scale? And why does it happen so abruptly in certain galaxies while others continue to thrive? One leading suspect is a brutal process called ram pressure stripping. Picture a galaxy hurtling through the supercluster like a ship plowing through choppy waters, except instead of waves, it's battling the thin, superheated gas that permeates galaxy clusters. As the galaxy moves, this intergalactic medium acts like a cosmic sandblaster, tearing away the cool hydrogen gas needed to birth new stars. Observations of Virgo galaxies like Messier 89 reveal this violence in action, their outer arms strewn with gas tails as if the galaxy itself is unraveling. The aftermath is eerie, a once vibrant spiral reduced to a passive red disk, its stellar nursery stripped bare. But here's where the mystery deepens. Not all red and dead galaxies show these scars. Some, like the massive ellipticals at Virgo's core, appear to have shut down from the inside out. This points to a different killer, internal quenching. Supermassive black holes at these galaxies' centers may have erupted in violent outbursts, flooding their surroundings with energy so intense it vaporized star-forming gas or blasted it into space. Others might have simply exhausted their fuel, aging into quiet retirement as their last generations of stars burned out. The puzzle grows richer when we compare these galaxies across cosmic time. In the early universe, red and dead galaxies were rare. Most systems were actively forming stars. Yet by the time the Virgo Supercluster took shape, something had flipped a switch. Was it the denser environment of the supercluster, with its frequent galaxy collisions and intense gravitational tides, that accelerated their demise? Or did these galaxies carry the seeds of their own destruction from birth, their fate sealed by some hidden property like dark matter composition or initial gas reserves? New data adds another twist. Some red galaxies in Virgo's outskirts show faint traces of recent star formation like embers flaring in dying fire. this suggests the shutdown isn't always permanent. Could a delayed influx of gas or a merger with a smaller galaxy briefly reignite star birth? If so, the line between dead and dormant may be thinner than we thought. What makes these galaxies so critical is what they reveal about cosmic life cycles. They're not just failed or exhausted, they're laboratories showcasing the extreme forces that shape galactic evolution. Whether strangled by their surroundings or starved from within, their stories warn us that even the mightiest galaxies aren't immortal. In the Virgo Supercluster, death isn't an end, it's a transformation, a silent rebellion against the universe's relentless push for creation. Stretching across 200 million light-years like a celestial scar, the Virgo overdensity defies simple explanation. This enormous river of stars winds through the supercluster, far too vast to be a mere stellar stream, yet lacking the organized structure of a traditional galaxy. Some researchers argue this cosmic oddity is the mangled remains of a dwarf galaxy, torn apart by Virgo's immense gravity. Others see it as evidence of a catastrophic collision, a tidal tale of stars ripped free during an ancient galactic merger. But neither theory fully accounts for its bizarre properties, leaving astronomers to grapple with a question that challenges our very definitions of what a galaxy can be. Look closely, and the overdensity stars tell conflicting stories. Their chemical compositions suggest two origins at once. Some stars bear the signature of an ancient, metal-poor environment, exactly what you'd expect from a primordial dwarf galaxy. Yet others appear surprisingly young and metal-rich, as if forged in the violent furnaces of a massive spiral like our Milky Way. This duality has sparked fierce debates. Could we be witnessing two phenomena superimposed: a disrupted dwarf entangled with debris from a separate collision? Or does this mixture point to something far stranger, like a galaxy that formed stars differently from any we've catalogued before? Adding to the confusion is the overdensity's motion. Unlike most tidal streams, which follow predictable orbits dictated by gravity, this structure moves against the current. Its stars travel almost perpendicular to Virgo's dominant flows, like salmon swimming upstream. Some theorists propose this could be evidence of a recent, high-speed encounter, perhaps a smaller galaxy cluster plowing through the supercluster's outskirts, leaving stellar wreckage in its wake. Others suggest the answer lies in dark matter, with invisible gravitational troughs funneling stars into this improbable configuration over billions of years. The most tantalizing clue comes from the overdensity's three-dimensional structure. When astronomers mapped its full extent using advanced sky surveys, they uncovered a shape resembling a corkscrew, a helical twist spanning thousands of light-years. Such intricate geometry is unheard of in known galaxy remnants. Simulations struggle to replicate it, whether modeling slow tidal disruptions or violent mergers. Could this be evidence of multiple overlapping events, like pages from different cosmic epochs pressed together? Or does it hint at undiscovered physics influencing how galaxies dissolve in dense environments? New radio telescope observations have added yet another layer. Hidden within the overdensity's starry veil are faint clouds of hydrogen gas moving independently from the stellar population. This gas shows shock fronts and temperature gradients unlike anything seen in typical galactic debris. Some researchers speculate these could be remnants of the original galaxy's interstellar medium, somehow preserved against all odds. Others argue they're fresh gas falling into the supercluster from intergalactic space, igniting brief flashes of star formation as they mingle with the ancient stellar river. What makes the Virgo overdensity so transformative isn't just its mystery, it's the questions it forces us to confront. At what point does a collection of stars stop being a galaxy and become something else entirely? How do we categorize structures that blur every boundary we've established? As telescopes grow more powerful, the overdensity's secrets may rewrite our understanding of galactic life cycles. For now, it stands as a testament to the universe's creativity, proof that even in death, galaxies can leave behind wonders that challenge our imagination. The spiral galaxy NGC 4522 isn't dying quietly. It's fighting for its life against an invisible cosmic storm. Racing through the Virgo Supercluster at nearly 2 million miles per hour, this majestic pinwheel of stars is being stripped bare, its precious star-forming gas ripped away by the superheated plasma that floods the space between galaxies. What makes this spectacle so extraordinary isn't just the violence of the process, it's that we're catching it in the act, witnessing a galaxy's transformation in real time. Hubble's sharp eye reveals the drama in stunning detail. NGC 4522's spiral arms, typically rich with glowing hydrogen clouds where new stars ignite, now appear frayed and tattered. But the true devastation lurks beyond visible light. Radio telescopes unveil colossal streamers of gas, some stretching over 60,000 light-years, trailing behind the galaxy like cosmic exhaust. These aren't gentle tendrils, they're the signatures of a brutal encounter where the intracluster medium acts like a sandblaster, scouring away the galaxy's future one atom at a time. The physics behind this stripping is both elegant and terrifying. As NGC 4522 plows through the supercluster, the tenuous but searing hot intergalactic gas collides with the galaxy's cooler molecular clouds. The difference in pressure is staggering. Imagine a snowflake hitting a blast furnace. Within these collision zones, the galaxy's gas isn't just pushed aside. It's superheated to millions of degrees, torn from gravity's grasp, and left to dissipate into the void. Yet amid this destruction, surprises emerge. ALMA millimeter wave observations detected pockets of stubborn molecular gas clinging to the galaxy's core, dense knots resisting annihilation. Some regions even show compressed gas at the galaxy's leading edge, briefly squeezed by the incoming pressure wave into fleeting bursts of star formation. It's as if NGC 4522 is squeezing out final generations of stars before the inevitable drought. What truly baffles astronomers is the galaxy's resilience. Current models predicted such ram pressure stripping would leave galaxies gas poor within 100 million years. Yet NGC 4522, despite losing gas for perhaps twice that long, still retains traces of its interstellar medium. This discrepancy hints at undiscovered replenishment mechanisms, perhaps cold gas raining down from invisible filaments or stolen reservoirs from smaller companion galaxies. The implications reach far beyond one galaxy's fate. NGC 4522 serves as a living laboratory for how environments shape cosmic evolution. Its ordeal mirrors what likely happened to many of Virgo's now red and dead galaxies, offering clues about why cluster galaxies age differently from their isolated counterparts. Every wisp of torn gas, every desperate starburst, writes another line in the universal codex of galactic survival, a code we're only beginning to decipher. Between the galaxies of the Virgo Supercluster, where darkness should reign absolute, there exists an ethereal glow, a whisper of light so faint it eluded detection for decades. This is intracluster light, the collective radiance of countless orphaned stars cast adrift in cosmic no-man's land. According to conventional wisdom, these stellar nomads should be rare, casualties of occasional galactic collisions. Yet observations reveal a ghostly sea of light up to 10 times brighter than models predict, forcing astronomers to confront a glaring discrepancy between theory and reality. The origins of these wandering stars turn out to be far more dramatic than anyone imagined. When galaxies collide, their gravitational tides don't just rearrange stars, they fling them into the void like sparks from a grinding wheel. But here's the catch: sophisticated simulations of galaxy mergers consistently produce fewer ejected stars than what we observe. Some regions of Virgo's intracluster space shine with the equivalent of several small galaxies worth of stars, yet the supercluster's merger history can't account for this stellar diaspora. Where did all these orphans come from? One radical possibility is that many weren't torn from galaxies at all, they formed in place. Deep imaging reveals the intracluster light isn't perfectly smooth but contains subtle knots and streamers. Some could be remnants of ancient, ultra-faint dwarf galaxies completely torn apart by tidal forces, leaving behind only their smeared starlight. Others might originate from a process called tidal threshing, where entire star clusters get stripped from galaxies during close encounters, dissolving into the intergalactic medium over billions of years. But the plot thickens when we examine the stars themselves. Spectroscopic analysis shows many intracluster stars are surprisingly metal-rich, suggesting they formed deep within galaxies before being ejected, yet their numbers still exceed theoretical ejection rates. This has led to provocative new models where galaxies in dense environments experience harassment, a relentless barrage of high-speed encounters that gradually peels away their outer stars like layers of an onion. Virgo's crowded core might be the perfect breeding ground for such phenomena, with gravitational interactions occurring far more frequently than in isolated regions of space. The implications ripple outward. Intracluster stars aren't just cosmic flotsam, they're tracers of the supercluster's violent history. Their distribution maps unseen gravitational forces, revealing where dark matter clumps distort spacetime. Some studies even suggest these stars might host rogue planets, creating an invisible archipelago of worlds forever cut off from galactic warmth. Perhaps most intriguing is what the light's brightness tells us about galaxy evolution. If current models underestimate stellar ejection by this margin, we may be missing fundamental physics about how galaxies interact. Alternative theories propose that intracluster stars accumulate gradually through countless minor mergers too faint to detect, or that certain types of dwarf galaxies are more fragile than we thought, dissolving entirely into the background glow. Each explanation carries consequences for how we understand the growth of cosmic structures. This faint luminescence between galaxies is more than just a mystery, it's a challenge to our narrative of how the universe builds and destroys. For every brilliant galaxy in Virgo's core, there may be 10 times as many stars drifting unseen in the darkness, a silent majority rewriting the story of the supercluster's past. Their very existence proves that the boundaries between galaxies are far more porous than we ever imagined, and that even in the void, light finds a way. The Virgo Supercluster holds a census problem that strikes at the heart of modern cosmology. According to our most sophisticated dark matter simulations, this region should be teeming with thousands of dwarf galaxies, small, faint companions orbiting larger galaxies like fireflies around a lantern. Yet when astronomers point their telescopes at Virgo, they find barely a tenth of the predicted number. This glaring mismatch between theory and observation, known as the missing satellites problem, isn't just a minor accounting error. It represents a fundamental challenge to our understanding of how the universe structures itself on the smallest scales. Digging deeper reveals just how perplexing this shortage truly is. Dark matter models suggest that every massive galaxy like our Milky Way should be surrounded by hundreds of dwarf satellites, relics from the earliest days of cosmic structure formation. These dwarfs would form within small clumps of dark matter, their faint starlight barely visible against the blackness of space. But in Virgo, where we have some of the deepest observations ever made, we're coming up dramatically short. Even accounting for the fact that many dwarfs would be too dim to detect, the numbers still don't add up, like finding a metropolis with only a handful of scattered villages when you expected bustling suburbs. Could the solution lie in our technological limitations? Some astronomers argue we're simply missing ultra-faint dwarfs hidden in the glare of brighter galaxies or lost in the daunting vastness of the supercluster. Recent advances support this idea. Sensitive surveys have begun uncovering a new population of almost invisible dwarfs in Virgo, galaxies so diffuse they appear as little more than wispy enhancements in the night sky. These ghosts often contain just a few thousand stars spread across volumes comparable to the Milky Way, making them nearly impossible to spot against the background glow of the universe. Yet even with these discoveries, we're still far from closing the gap. This discrepancy has led some theorists to question the very nature of dark matter itself. The prevailing cold dark matter model assumes dark matter particles move sluggishly, allowing them to clump readily into the small-scale structures that would host dwarf galaxies. But what if dark matter is warmer, moving fast enough to smooth out these tiny density fluctuations? Warm dark matter models do predict fewer dwarfs, potentially solving the mystery. However, they also struggle to explain other observed features of cosmic structure, leaving astronomers to wonder if the truth lies somewhere in between. An alternative explanation paints a far more violent picture. Perhaps Virgo's dense environment is actively destroying dwarfs as we watch. Computer simulations show that when small galaxies venture too close to their massive neighbors, tidal forces can shred them apart over billions of years, leaving behind only streams of stars as tombstones. Some researchers speculate that what we're seeing isn't a lack of formation, but an excess of destruction, a cosmic battlefield where only the hardiest dwarfs survive. Supporting this, Virgo's remaining dwarfs show peculiar traits. Many are preferentially found far from the cluster's center, as if the inner regions have been systematically cleared of fragile systems. The implications reach far beyond galaxy counts. Dwarf galaxies are crucial testing grounds for dark matter theories because their simple structures and strong gravity make them exceptionally sensitive probes. If our models can't accurately predict their numbers and distributions, what else might we be getting wrong about the universe's scaffolding? Every newly discovered ultra-faint dwarf, or absence where one should be, carries clues about physics operating on scales we can't replicate in any laboratory. What makes this mystery particularly tantalizing is that the solution might require us to rethink multiple aspects of astrophysics simultaneously. Maybe dark matter interacts with itself in unexpected ways, or perhaps early universe conditions suppressed dwarf formation more than we realized. There's even speculation that some missing dwarfs never formed stars at all, existing today as pure dark matter halos undetectable by conventional means. As telescopes grow more sensitive and simulations more sophisticated, the Virgo Supercluster continues to serve as the ultimate testing ground, a place where the faintest glimmers might illuminate our deepest cosmic questions. Streaking through the Virgo Supercluster like a comet through fog, the galaxy M86 drags behind it a cosmic contrail of staggering proportions, a 300,000 light-year long plume of gas glowing faintly against the void. This isn't just any galactic tale, it's one of the most extreme examples of interstellar material being ripped from its home, raising urgent questions about what forces could produce such a spectacular trail. But the mystery isn't just in the plume's existence, it's in the details that defy easy explanation. Ram pressure stripping seems the obvious culprit at first glance. As M86 barrels through the supercluster's intracluster medium at over 4 million miles per hour, the searing hot gas between galaxies should act like a cosmic wind, tearing away the cooler hydrogen-fueling star formation. Yet when astronomers mapped the plume's structure, they found peculiar inconsistencies. Instead of the smooth, tapered tail expected from steady stripping, the gas forms chaotic knots and filaments, with some regions denser than the galaxy's own disk. Even stranger, the plume's temperature varies wildly, pockets of gas chilling to near absolute zero alongside others heated to millions of degrees. This isn't the clean surgical removal ram pressure usually performs. It's more like a galactic mugging, leaving behind clues of a far more violent encounter. That's where the slingshot hypothesis takes center stage. Some researchers argue M86's plume bears the scars of a close gravitational encounter with Messier 84, another massive galaxy it passed roughly 200 million years ago. Simulations suggest such an interaction could have launched a tidal wave of gas outward, stretching it into this extraordinary stream, the telltale sign. The plume's curvature matches predictions for material yanked backward during a high-speed flyby, a cosmic crack-the-whip effect where gravity's pull distorts rather than cleanly shears. But skeptics point out a problem: the timing doesn't quite align. If the plume originated from that encounter, its oldest stars should show different velocities than what's observed. Unless, of course, multiple forces are at work simultaneously. New evidence from X-ray telescopes complicates the picture further. Deep imaging reveals the plume isn't just gas, it's studded with faint X-ray sources, likely black holes or neutron stars flung from the galaxy during the chaos. Their presence suggests the stripping process didn't just remove diffuse gas but tore entire star systems from their orbits. Even more puzzling are the plume's magnetic fields. Polarization measurements show the fields are far more organized than expected, twisted into helical patterns that imply powerful electromagnetic forces shaping the debris. Could M86's supermassive black hole have played a role, its jets injecting energy into the plume like a cosmic mixer? The stakes here extend far beyond one galaxy's dramatic exit. If ram pressure dominates, it implies the supercluster's intracluster medium is denser and more turbulent than models suggest. But if gravitational interactions are the primary driver, we may be underestimating how often massive galaxies graze past each other in these crowded neighborhoods. Every quirk of this plume, from its icy patches to its magnetic braids, offers a piece of the puzzle. For astronomers, M86 isn't just a galaxy leaving a trail. It's a laboratory for the most extreme forces shaping our universe, proving that even in the vastness of space, nothing escapes without consequences. The Virgo Supercluster isn't just drifting through the cosmos, it's racing toward an unseen destination with a velocity that defies conventional physics. Every galaxy within its vast domain, including our own Milky Way, is caught in this relentless current, pulled toward something called the Shapley Attractor at a staggering speed of over 600 kilometers per second. But here's the twist. When astronomers tally up all the visible matter along this path, the galaxy clusters, the superclusters, even the diffuse gas, the gravitational pull falls far short of explaining such violent motion. It's as if the universe has hidden an entire mountain range behind a curtain, and we're only seeing the foothills. One possible explanation lies in the realm of dark matter. If enormous, unseen concentrations of this mysterious substance lurk along our trajectory, their gravity could account for the supercluster's unexpected haste. Observations of other cosmic flows hint at this possibility, vast rivers of galaxies all streaming toward common points, as if drawn by invisible hands. Yet even the most generous estimates of dark matter's distribution struggle to reconcile the numbers. The discrepancy is so glaring that some researchers have begun questioning whether we're missing something fundamental about gravity itself. This is where modified Newtonian dynamics, or MUND, enters the conversation. The theory proposes that gravity behaves differently on cosmic scales than Einstein's equations predict, eliminating the need for dark matter entirely. In MUND framework, the Virgo supercluster's motion might not require hidden mass, just a recalibration of how we calculate gravitational attraction in low acceleration environments. Supporters point to certain dwarf galaxies whose rotations align better with MUND than standard models. But skeptics fire back. If MUND were the answer, why do some galaxy clusters still exhibit motions that demand unseen mass? The debate rages on, with Virgo's inexplicable velocity serving as a battleground for these competing worldviews. Complicating matters further is the Shapley Attractor itself. This distant concentration of galaxy clusters, one of the most massive structures in the observable universe, might not be the final destination. Recent surveys suggest something even grander lies beyond it, a gravitational anomaly so immense it tugs at Shapley like a marionette string. Could this hypothetical great attractor's big brother explain Virgo's excess speed, or does its existence only deepen the mystery, pushing the missing mass problem to even larger scales? What makes this cosmic chase so pivotal is what it reveals about our place in the universe. We're not just passengers on a random drift, we're part of a vast migration, swept along by forces we can't fully see or understand. Whether the solution lies in dark matter, revised gravity, or something entirely unforeseen, the Virgo Supercluster's unexpected motion reminds us that the cosmos still holds cards close to its chest. Every measurement, every new map of large-scale flows brings us closer to answers, or perhaps to even bigger questions. Floating in the cosmic voids between Virgo's galaxies, there exists something that shouldn't be there: vibrant pockets of blue light, each one a bustling nursery of newborn stars untethered from any galaxy. Astronomers call them blue blobs, and they're rewriting the rules of where and how stars can form. These isolated fireballs defy expectation, burning brightly in regions so empty they were long considered stellar deserts. How did these celestial oases come to be, and what secrets do they hold about the supercluster's turbulent history? The most striking examples, like the famous Virgo 21, glow with the intensity of thousands of young, hot stars, the kind typically found only in the spiral arms of galaxies. Yet here they are, adrift in intergalactic space like ships without harbors. Spectroscopy reveals their composition mirrors the gas clouds of large galaxies, rich with the heavier elements forged in stellar furnaces. This presents a paradox. Normally, such enriched gas requires multiple generations of stars to seed it with metals, a process thought impossible far from galactic cores. One explanation is as dramatic as it is violent. These blobs may be the scattered remains of galaxies torn apart by Virgo's gravitational tides, their star-forming gas ejected during collisions only to later collapse under its own weight. But alternative theories challenge even this narrative. Some blobs show chemical signatures too pristine for recycled material, suggesting they formed from ancient reservoirs of primordial gas leftovers from the supercluster's birth that somehow avoided being absorbed into galaxies. Deep radio observations reveal faint filaments connecting certain blobs to nearby galaxies, like umbilical cords of hydrogen gas. These could be trails left by ram pressure stripping, where gas was ripped from galaxies during high-speed passages through cluster plasma, then later ignited by shock waves or dark matter perturbations. The real surprise came when astronomers measured the blob's motion. Instead of drifting aimlessly, many are racing through the supercluster at speeds that shouldn't allow star formation at all. Normally, gas moving this fast would be too turbulent to collapse into stars. Yet somehow, these regions have overcome the odds, hinting at unknown stabilizing mechanisms. One possibility involves dark matter microhalos, invisible gravitational anchors that provide just enough pull to calm the chaos. Another points to magnetic fields threading through the gas, acting like cosmic scaffolding to support stellar birth. What makes the blobs truly transformative is their potential to rewrite galactic life cycles. If stars can form this efficiently in the void, then traditional boundaries between galaxies and intergalactic space blur. Some researchers speculate these regions might be the seeds of future ultra-diffuse galaxies, while others propose they're temporary flares doomed to fade once their gas exhausts. Every new discovery adds complexity, from blobs with multiple stellar generations suggesting prolonged activity, to others with bizarre planetary nebulae indicating advanced stellar evolution in isolation. These celestial nomads prove that star formation isn't confined to galaxies. It's a universal phenomenon that can spark anywhere the conditions whisper yes. In the Virgo Supercluster, the blue blobs are more than oddities. They're rebel outposts challenging our cosmic maps, reminding us that the universe thrives in the places we least expect. The M49 galaxy appears serene from afar, a smooth golden ellipse floating in Virgo's depths, its stars evenly distributed like dust in a still pond. But peel back the illusion of symmetry, and this cosmic giant reveals a striking secret. Its dark matter halo isn't just lopsided, it's been torn apart. While most massive galaxies anchor their dark matter in spherical shells, M49's invisible scaffolding stretches asymmetrically, bulging toward one side as if yanked by an unseen force. This isn't just a quirk of nature, it's evidence of a violent past, a gravitational wound that never fully healed. Deep imaging tells the story of a catastrophic encounter. The galaxy's outer stars show peculiar velocity patterns streaming in arcs that suggest a smaller galaxy was shredded and absorbed long ago. Normally, such mergers would eventually smooth out, with dark matter redistributing evenly over billions of years. Yet M49's halo remains stubbornly unbalanced, implying the collision occurred relatively recently by cosmic standards, perhaps less than 2 billion years ago. The intruder galaxy didn't just donate stars, it delivered a gravitational punch that still distorts M49's core structure today. What makes this asymmetry so puzzling isn't just its persistence, but its scale. The densest part of the dark matter halo extends nearly twice as far on one side of the galaxy compared to the other, a mismatch that challenges our models of how dark matter behaves during mergers. Simulations suggest such lopsidedness should be temporary, as dark matter's lack of friction ought to let it slosh back into equilibrium faster than visible matter. Yet M49 defies these expectations, hinting that dark matter might interact with itself in ways we haven't accounted for, perhaps through weak forces beyond gravity, or complex particle physics that leaves lasting imprints on cosmic structures. The smoking gun lies in the galaxy's globular clusters. These ancient star swarms orbit like bees around a hive, tracing the contours of M49's gravitational field. Their distribution mirrors the dark matter's asymmetry, with clusters on the galaxy's heavy side orbiting faster and more erratically than those elsewhere. Some even appear to be recent additions captured from the devoured dwarf, still clinging to their original trajectories like survivors refusing to assimilate. But the plot thickens when we examine M49's core. At its heart lies a supermassive black hole, but one that's curiously offset from the galactic center. This displacement aligns eerily with the direction of the dark matter bulge, as if both were yanked by the same gravitational hand. Some theorists propose the black hole is still wobbling from the merger's impact, its oscillations gradually damping as it settles, a process that could take billions more years. Others suggest the entire galaxy is undergoing a slower, more complex realignment, with dark matter leading the dance while stars lag behind. The implications ripple far beyond one galaxy's odd shape. If mergers can leave dark matter halos permanently lopsided, it means our census of cosmic mass might be systematically skewed. What appears to be missing mass in some regions could simply be displaced. More profoundly, M49 offers a rare laboratory to study dark matter's particle properties through its gravitational aftermath. Every star cluster's orbit, every warp in the halo's shape, encodes clues about how this mysterious substance responds to violence, whether it rebounds like a fluid, resists like a gel, or does something entirely unexpected. In the grand tapestry of the Virgo Supercluster, M49 serves as a reminder that equilibrium is the exception, not the rule. Galaxies don't evolve in isolation. They bear the scars of their encounters, their asymmetries whispering stories of long-ago collisions. What we perceive as a calm, golden ellipse is really a cosmic seismograph, still registering tremors from an ancient cataclysm that reshaped not just stars, but the very fabric of the unseen universe. Deep within the heart of the Virgo cluster, astronomers have discovered a cosmic paradox, vast weather systems where the rules of physics seem to bend. These aren't storms of wind or rain, but titanic cold fronts sculpted from superheated gas, stretching millions of light years across the intracluster medium. Picture an ocean current so immense it could swallow galaxies whole, yet instead of turbulent mixing, its boundaries remain knife-sharp, like an invisible wall separating a raging inferno from a frigid void. The temperatures involved defy intuition. On one side of these fronts, gas simmers at nearly 80 million degrees, while just a short cosmic distance away, it plunges to a mere 20 million degrees. Such extreme gradients should vanish instantly, hot and cold gases mixing like cream in coffee. Yet these structures persist for billions of years, their edges crisp as frost on a window pane. How can something so violent remain so ordered? One clue lies in the front's motion. Observations from X-ray telescopes like Chandra reveal these boundaries aren't static. They're racing through the cluster at over 1,000 kilometers per second. Simulations suggest they form when smaller galaxy groups plow into the main cluster, creating shock waves that ripple through the intracluster medium like sonic booms. Normally, these shocks would dissipate quickly, but Virgo's dense environment and powerful magnetic fields appear to wrap the cold fronts in invisible sheaths, preventing thermal erosion. It's as if the universe has woven cosmic insulation around these structures, preserving their integrity against all odds. Magnetic fields might hold the key to the mystery. Threading through the cluster like an invisible spiderweb, these fields could suppress turbulence at the edges of cold fronts, acting like a barrier that prevents hot and cold gases from mingling. Supporting this, X-ray images show filamentary patterns along the front's telltale signs of magnetic braids channeling the gas's flow. Some researchers even speculate that dark matter plays a role, its gravity subtly shaping the intracluster medium in ways we're only beginning to understand. Yet the most baffling aspect isn't just the front's longevity, it's their complex substructure. High-resolution data reveals finer layers within the gas, like nested thermal waves frozen in time. Some exhibit steps where temperature drops occur in discrete jumps rather than smooth gradients, hinting at previously unknown plasma physics operating at colossal scales. Others show signs of Kelvin-Helmholtz instabilities, the cosmic equivalent of wind shear, yet these turbulent curls somehow don't destroy the overall structure. What makes these cold fronts invaluable is what they reveal about energy transfer in the universe. They're natural laboratories for studying how heat moves in environments where conduction and convection behave nothing like they do on Earth. Every sharp boundary, every unexpected temperature spike, challenges our assumptions about how matter behaves under extreme conditions. Some theories now suggest these structures might even act like cosmic refrigerators, redistributing heat across the cluster in ways that influence star formation and galaxy evolution. In Virgo's depths, these ancient thermal fossils drift like relics of forgotten collisions, their persistence a testament to the delicate balance between chaos and order. They remind us that even in the most energetic realms of the universe, there are pockets where nature imposes rules we've yet to fully decipher, where the simple act of cooling becomes a cosmic mystery written in X-rays and magnetic fields. Gazing at NGC 4438 is like staring into the eyes of cosmic violence, two brilliant cores gleaming from a single galaxy, their glow separated by a gulf of twisted starlight. This striking eyes formation didn't emerge from peaceful evolution. It's the aftermath of a gravitational ambush so fierce it reshaped an entire galaxy's architecture. The scars of this collision ripple across 60,000 light-years, from the warped spiral arms to the vast plumes of hydrogen gas torn loose and cast adrift. But unraveling this celestial crime scene presents astronomers with a dilemma. Was the perpetrator the neighboring NGC 4435, or is there an unseen interloper still lurking in the shadows? The evidence against NGC 4435 seems compelling at first glance. Just 40,000 light-years away, a stone's throw by galactic standards, this compact galaxy bears its own marks of violence. Its outer stars are strewn into elongated streams, as if it too was wrenched by the same encounter. Computer simulations show that a close pass between these two could explain many of NGC 4438's injuries. The dual nuclei may be the remnants of its original core and a cluster of stars ripped from the intruder, now orbiting each other like boxers after a brutal exchange. Supporting this, infrared observations reveal dust lanes between the galaxy's cosmic fingerprints left by their gravitational tug of war. Yet inconsistencies in the case suggest a more complex narrative. For one, the velocity of debris expelled from NGC 4438 exceeds what a collision with NGC 4435 alone could produce. Some gas clouds are racing outward at over 700 kilometers per second speeds typical of a far more catastrophic impact. Even stranger, the angles of these ejections don't align with a straightforward encounter between the two visible galaxies. It's as if a third, darker player delivered a sucker punch before vanishing into the cosmic night. This is where the mystery deepens. Radio telescopes have detected faint hydrogen clouds drifting near the scene, orphaned gas with no apparent owner. Their motion suggests they were stripped from an object several times more massive than NGC 4435. Could these be the remnants of a now-defunct dwarf galaxy, one that plunged through NGC 4438's heart before disintegrating? Or perhaps evidence of a high-speed flyby from a rogue galaxy now far beyond our view? The Virgo cluster's crowded environment makes such ghostly assailants plausible, with hundreds of dim galaxies potentially slipping past our surveys. Adding to the intrigue are the black holes at the center of this drama. NGC 4438's dual nuclei both emit X-rays, signaling the presence of active supermassive black holes, a rarity for a galaxy of its size. One theory posits that the second black hole was delivered during the collision, either from the intruding galaxy's core or as part of a star cluster hurled into the chaos. If so, we may be witnessing the early stages of a slow-motion merger, where two black holes will eventually spiral together over millions of years, shaking space-time itself with gravitational waves. What makes this cosmic detective story so pivotal is what it reveals about galactic resilience. Despite the violence, NGC 4438 hasn't been shattered, it's adapting. New stars ignite in the compressed gas along its distorted arms, while its surviving dust lanes funnel material toward the black holes, feeding fresh outbursts of energy. The galaxy is a testament to how even the most brutal encounters can spark rebirth, forging new structures from the wreckage of the old. Every telescope trained on these gleaming eyes peels back another layer, not just of this collision, but of the untold others shaping the Virgo Supercluster's turbulent history. The Virgo Supercluster isn't just a crowded metropolis of galaxies, it's also home to staggering cosmic deserts, regions so empty they challenge our understanding of how the universe structures itself. These voids, some spanning over 100 million light-years, aren't simply quiet neighborhoods with fewer stars, they're near-total vacuums where galaxies are almost entirely absent, like bubbles of nothingness floating in the cosmic web. What makes these gaps so baffling isn't their existence, but their extreme emptiness and the question of whether they've been barren since the dawn of time, or were violently emptied by forces we're just beginning to comprehend. One of the most startling examples lies between the Virgo cluster and the Fornax cluster, a void so vast that if our Milky Way sat at its center, we'd see fewer than a dozen galaxies in any direction with the naked eye. Mapping these regions reveals their edges are unnaturally sharp, as if some invisible scalpel carved them out of the cosmic fabric. According to standard models of structure formation, tiny quantum fluctuations in the early universe should have left voids with gently sloping density gradients. not these cavernous, sharply defined absences we observe. Some theorists argue this points to primordial conditions far stranger than we've accounted for, where dark matter or dark energy played unexpected roles in sculpting space before galaxies even formed. Yet there's another, more unsettling possibility. What if these voids weren't always empty? Observations of galaxies near void boundaries show peculiar velocity patterns. Many are receding from the voids as if pushed outward by some repulsive force. This has led to provocative theories involving dark energy, the mysterious substance accelerating the universe's expansion. In most of the cosmos, dark energy's effects are subtle, barely noticeable over galactic distances. But in these voids, where matter's gravitational pull is weakest, dark energy might dominate completely, creating an expansive pressure that actively cleared the regions over billions of years. Imagine a cosmic game of musical chairs where the chairs themselves are being pushed apart before anyone can sit down. The void's contents deepen the riddle. While most appear truly empty, a rare few harbor void galaxies, isolated star systems drifting alone in the darkness. These loners show bizarre traits. Many are unusually rich in gas yet poor in metals, as if they've been cut off from the galactic recycling process for eons. Some even rotate backward compared to their expected motion, hinting at ancient gravitational disturbances that sent them spiraling into the void. Their very existence challenges both the primordial and clearing theories. Why would any galaxy survive if dark energy aggressively purged these regions? Perhaps the most compelling clues come from the void's arrangement. They aren't randomly scattered. Many align along faint radio-emitting filaments that trace the supercluster's hidden scaffolding. These void filaments suggest the gaps might be connected through an unseen network, like chambers in a hive. Intriguingly, some align with mysterious cold spots in the cosmic microwave background, regions of the early universe that were slightly cooler than their surroundings. Could these temperature differences mark the seeds of today's voids, frozen echoes of the universe's first trillionths of a second? The implications ripple beyond cosmology. If voids were actively cleared, it would mean the universe's large-scale structure is still evolving in ways we've barely begun to model. If they're primordial, they could preserve information about inflationary physics impossible to study elsewhere. Every cubic megaparsec of emptiness whispers questions. Are voids truly empty or filled with some dark component we can't detect? Do they contain rogue planets or wandering black holes ejected from galaxies eons ago? The Virgo Supercluster's gaps aren't just absences, they're puzzles written in negative space, challenging us to read between the lines of the cosmic ledger. At the heart of the M60 galaxy, two cosmic titans circle each other in a silent, slow-motion dual supermassive black holes, locked in a gravitational embrace so tight they could span the distance between Earth and Pluto with room to spare. These aren't just any black holes, their combined mass nears 4 billion suns, making their dance one of the most massive binary systems ever discovered. What makes this pairing extraordinary isn't just their size. It's the fact they've been orbiting for billions of years without merging, defying expectations about how black holes evolve in galactic cores. X-ray telescopes first spotted the telltale flicker, two distinct sources of high-energy light pulsing from M60's center, separated by less than 1 light-year. Normally, black holes this close should have spiraled together long ago, their collision rippling spacetime with gravitational waves. Yet here they persist, their orbit decaying far slower than physics predicts. The leading theory points to their environment. M60 sits in a densely packed region of the Virgo cluster, where frequent galactic interactions may have funneled excessive gas and stars into the black hole's vicinity. This cosmic buffet could be acting like a gravitational brake, their shared accretion disk creating drag that postpones the inevitable collision. But there's a twist. Recent radio observations reveal vast jets of particles shooting from only one of the black holes, an asymmetry that hints at wildly different feeding habits. While one gorges on surrounding matter, its sibling appears starved, possibly explaining their stalled merger. Without equal friction from infalling material, their orbital decay may have hit a cosmic traffic jam. Some simulations even suggest their surrounding gas forms a lopsided torus, exerting uneven forces that keep them suspended in this precarious balance. The implications of their eventual collision when it finally happens are staggering. When two supermassive black holes merge, they become the universe's most powerful gravitational wave generators, shaking spacetime with energy surpassing all the stars in the observable universe combined. M60's pair offers a rare preview of this cataclysm. Their delayed merger might also explain why we've detected fewer supermassive black hole collisions than predicted. Perhaps many binaries enter this prolonged stalemate, their final crashes spaced further apart than models assumed. What astronomers wouldn't give to witness the moment these behemoths finally unite? The resulting kick could send the newborn black hole rocketing through its galaxy at thousands of kilometers per second, a runaway bullet tearing through M60's stellar fabric. Or perhaps the merger will unleash a quasar, flooding the Virgo cluster with light so intense it outshines every star in the supercluster combined. Until then, this sluggish waltz continues, a cosmic countdown to one of the universe's most violent and illuminating spectacles. Hovering on the edge of the Virgo cluster like a cosmic ghost, Virgo E21 taunts astronomers with its impossible contradiction. An object so rich in hydrogen gas it should be birthing stars by the thousands, yet utterly devoid of starlight. This so-called dark galaxy floats unseen, detectable only by the faint radio whispers of its atomic hydrogen, a vast reservoir of fuel stretching over 40,000 light-years with no stars to burn it. Is this the smoking gun for dark matter's invisible architecture, or just an elaborate cosmic mirage? The debate cuts to the heart of how galaxies form and what might be missing from our cosmic inventory. One camp sees Virgo E21 as the holy grail of dark matter research, a pristine halo where gas gathered but stars never ignited. According to leading theories, dark matter's gravitational scaffolding should seed thousands of such structures, each cradling gas but lacking the density to spark stellar fires. The object's rotation curve, mapped by hydrogen emissions, shows the telltale signature of dark matter's grip. Gas orbits too fast for the visible mass alone, implying an unseen gravitational anchor. If confirmed, Virgo E21 would be the first uncontested example of a failed galaxy, offering a direct window into how dark matter molds the universe behind the scenes. Yet skeptics paint a different picture. They argue the hydrogen cloud could be tidal debris, gas ripped from a passing galaxy during a violent encounter, stretched into this phantom shape by gravitational forces. Supporting this, deep imaging reveals faint stellar streams nearby, possible remnants of the collision that birthed Virgo E21, the real nail in the coffin. Some models suggest the cloud's hydrogen distribution is too lumpy for a stable dark matter halo, with density variations better explained by a one-time galactic car crash. The plot thickens when we examine the gas itself. Unlike typical interstellar hydrogen, Virgo E21 emissions show peculiar velocity twists, knots of gas moving against the overall rotation. These could be turbulence from an ancient impact or signs of internal dynamics in a dark matter framework. Even stranger, the cloud's metallicity, the trace elements mixed with its hydrogen, is mysteriously low. Pristine gas from the early universe would match this, but so would gas stripped from a galaxy's outer edges where fewer stars have enriched the environment. New observations add fuel to the fire. Recent ultra-deep optical surveys detected a smattering of dim stars within Virgo E21 bounds, just enough to question the pure dark galaxy label. Yet these stars may be interlopers unrelated to the cloud's true nature. Meanwhile, gravitational lensing studies search for the subtle warping of background light that would betray dark matter's presence, but results remain frustratingly inconclusive. The stakes transcend one enigmatic object. If Virgo 21 is a dark galaxy, it implies hundreds more could lurk undetected, rewriting our census of cosmic structures. If it's debris, it reveals how efficiently clusters like Virgo can shred galaxies and hide the evidence. Every telescope trained on this radio whisper brings us closer to an answer or deeper into the mystery. For now, Virgo 21 lingers in the shadows, a cosmic Rorschach test challenging us to decide what we're really seeing, a fundamental building block of the universe, or the ghostly aftermath of a forgotten collision. The Virgo cluster isn't just a hub of visible wonders, it's also leaking an invisible torrent of gamma rays, high-energy photons that crackle with mysteries we've only begun to decode. NASA's Fermi Large Area Telescope first picked up this gamma-ray excess, a diffuse glow of radiation bathing the cluster at energies that shouldn't exist in such abundance. Picture a cosmic bonfire where no one lit a match, a blaze of particles with no obvious fuel source. The puzzle isn't just the radiation itself, but its peculiar fingerprint, a spectrum that peaks at energies around 2 gigaelectronvolts, a range that defies simple explanations. One tantalizing possibility ties this excess to dark matter's elusive nature. Certain theoretical particles like WIMP, weakly interacting massive particles, could annihilate upon collision, transforming into gamma rays in a final flash of existence. If this is happening in Virgo, it would mean we're indirectly glimpsing dark matter's shadowy interactions, a process that could reveal its mass and behavior for the first time. Supporters of this idea point to the excess's smooth distribution across the cluster, matching predictions for dark matter's spread. Yet skeptics counter with a glaring inconsistency. The signal's intensity is far stronger than most models predict, as if dark matter is annihilating at rates that defy conventional physics. But there's another contender in this cosmic whodunit: pulsars. These rapidly spinning neutron stars, stellar corpses left behind by supernova, emit gamma-ray beams like interstellar lighthouses. Hidden populations of millisecond pulsars, too faint to detect individually, could collectively produce the observed glow. Recent analyses reveal tantalizing hints of point-like sources embedded within the excess, suggesting unresolved pulsars might be lurking just below Fermi's detection threshold. If true, it would mean Virgo's gamma rays stem from ordinary astrophysics, not exotic particles, a letdown for dark matter hunters, but a breakthrough in understanding pulsar demographics. The plot thickens when we examine the excess's precise location. Unlike dark matter, which should halo the entire cluster uniformly, the gamma rays show subtle concentrations near massive galaxies like M87. This could imply a hybrid explanation: dark matter annihilation boosted by the gravitational wells of these giants, or pulsars clustered in their tidal streams. Alternatively, there might be entirely new physics at play: decaying action-like particles, primordial black holes evaporating into radiation, or even flaws in our understanding of how gamma rays propagate through intergalactic space. What makes this mystery so pivotal is its potential to crack open multiple cosmic enigmas at once. If the excess confirms dark matter's particle nature, it would rank among the most profound discoveries in physics. If pulsars are the culprits, it forces us to rethink how these objects form and distribute in dense environments. And if the answer lies elsewhere entirely, well, that's the thrill of Virgo, a supercluster that refuses to fit neatly into our models, reminding us that the universe's most energetic secrets often hide in plain sight. Spiraling through the Virgo cluster with graceful arms that once blazed with stellar nurseries, the galaxy NGC 4569 now stands as a cosmic paradox, a majestic spiral that forgot how to spin new stars. Unlike most galaxies of its size and type, which continue birthing stars at a leisurely pace, this cosmic pinwheel has seen its star formation quenched so abruptly that astronomers compare it to a waterfall suddenly frozen mid-cascade. The clues to this shutdown aren't just written in the galaxy's present state, but etched across its turbulent history, offering a masterclass in how environments can strangle even the most vibrant galaxies. One glance at NGC 4569's surroundings reveals the prime suspect, the Virgo cluster's searing intracluster medium. This superheated gas, thin as Earth's exosphere but millions of degrees hotter, acts like a cosmic sandblaster against galaxies moving through it. As NGC 4569 plunges through this plasma at nearly 4 million miles per hour, the pressure strips away its cool hydrogen fuel, the very gas needed to form new stars. Radio telescopes have caught this violence in action, imaging vast tendrils of hydrogen trailing behind the galaxy like a comet's tail, each wisp representing enough raw material to build millions of stars. Yet despite losing this colossal reservoir, the galaxy shows few signs of the dramatic starbursts typically seen when gas is compressed by such encounters. It's as if the star-making machinery didn't just stall, it vanished entirely. But the plot twists when we peer closer. Deep infrared observations reveal that NGC 4569 hasn't just been stripped, it's been robbed. The galaxy's outer regions are littered with orphaned star clusters and distorted streams of stars, evidence of a gravitational mugging that likely occurred before it entered Virgo's core. Simulations suggest a close encounter with the massive galaxy Messier 87, Virgo's dominant member, could have wrenched away much of NGC 4569's gas long before ram pressure finished the job. This 1-2 punch gravitational theft followed by environmental stripping may explain why the galaxy's quenching was so absolute, leaving it with neither the fuel nor the mechanism to reignite star birth. The smoking gun lies in the galaxy's core, while most stripped spirals retain dense nuclear gas reserves that allow limited star formation near their centers. NGC 4569's heart is eerily quiet. Millimeter-wave telescopes detect only trace amounts of molecular gas, and what little remains shows bizarre turbulence, as if stirred by some unseen force. Some researchers point to the supermassive black hole at the galaxy's center, theorizing that past outbursts might have heated or expelled its remaining fuel. Others propose a more subtle culprit, the galaxy's own magnetic fields, which could have stabilized its gas against collapse long enough for environmental forces to permanently disrupt it. Yet the most tantalizing clue comes from the galaxy's surviving stars. Their demographics reveal an unnatural gap, a near-total absence of stars younger than about 500 million years, as if someone flipped a switch to halt production. This timeline aligns eerily with NGC 4569's estimated arrival in Virgo's inner cluster, suggesting the shutdown wasn't gradual but catastrophic. Unlike other red and dead galaxies that faded slowly over billions of years, this spiral appears to have crossed some critical threshold where its star-forming potential wasn't just diminished but erased. What makes NGC 4569 so transformative isn't just its own fate, it's a preview of what awaits countless other galaxies as they drift into dense cosmic environments. Its story forces us to confront how galaxies die, not always with a slow dimming, but sometimes with a swift, violent silencing. Every observation peels back another layer, revealing not just how environments shape galaxies, but how those galaxies carry scars from every chapter of their journey. In the grand narrative of the Virgo Supercluster, this quenched spiral is more than an anomaly. It's a prophet whispering warnings about the delicate balance between creation and destruction in an ever-evolving universe. In the vast cosmic dance of the Virgo Supercluster, astronomers have stumbled upon a choreography so precise it defies randomness, galaxies spinning in uncanny alignment. their rotation axes pointing in eerily similar directions like compass needles drawn to some invisible north. This phenomenon, observed across tens of millions of light years, suggests a level of coordination that shouldn't exist in a universe governed by chaos and local forces. The odds of such alignment occurring by chance are astronomically slim, raising a profound question: what cosmic hand orchestrated this synchronized spin? One compelling explanation reaches back to the universe's infancy, when the seeds of these galaxies first formed. During these primordial moments, the cosmos was threaded with vast magnetic fields, invisible lines of force woven through the fabric of space itself. These fields, generated in the turbulence of the Big Bang's aftermath, could have imprinted a preferred direction on collapsing gas clouds, guiding their rotation as they condensed into galaxies. Like iron filings aligning to a magnet, the nascent galaxies might have inherited their spin from these ancient magnetic whispers, preserving the alignment over billions of years. Supporting this idea, simulations show that sufficiently strong primordial fields could indeed couple with protogalactic gas, creating coherent spin axes on astonishingly large scales. Yet magnetism isn't the only suspect. Another theory points to the supercluster's tumultuous youth, when rivers of gas and dark matter flowed along cosmic filaments, funneling material into the growing Virgo structure. These flows weren't random, they followed the gravitational contours of the early universe, creating coherent motions that might have set galaxies spinning in harmony. Picture a leaf caught in a river's current, its rotation influenced by the water's unified pull. If galaxies formed within such directed streams, their angular momentum could have locked into alignment, a fossilized record of the supercluster's violent assembly. The evidence grows stranger when we examine which galaxies obey this rule and which defy it. Dwarf galaxies, the smaller and more numerous members of the supercluster, show far less alignment than their massive counterparts. This disparity hints that the mechanism behind the spin coherence operates selectively, perhaps requiring galaxies of a certain size or formation history to fall in line. Even among the aligned giants, there's a puzzling gradient. Galaxies nearer the supercluster's core exhibit tighter synchronization than those on the outskirts, suggesting environmental forces might reinforce the pattern over time. Critics of these theories raise valid counterpoints. If primordial magnetic fields were strong enough to align galaxies, why haven't we detected their residual imprint more clearly in the cosmic microwave background? And if large-scale flows are the culprit, why don't all superclusters show similar spin coherence? These questions have led to more radical proposals, including the influence of undiscovered fundamental forces or exotic physics in the early universe that briefly coupled galaxy spins before fading from view. The implications ripple far beyond Virgo. If galaxy spins can be synchronized across such vast distances, it challenges our understanding of how cosmic structures influence one another. It suggests that the universe operates on scales of organization we're only beginning to glimpse, where connections forged in the first moments of time still resonate today. Every measurement of a galaxy's rotation, every new map of magnetic fields in deep space, brings us closer to answering whether this alignment is a quirk of Virgo or a universal phenomenon waiting to be uncovered. What makes this celestial synchronicity so mesmerizing isn't just the mystery of its origin, but what it reveals about the universe's hidden architecture. The Virgo supercluster may appear as a scatter of isolated islands, but beneath the surface there's a rhythm, a silent, spinning harmony written in the language of galaxies. Most black holes in the universe are messy eaters belching out chaotic jets of particles in fits and starts as they devour their surroundings. But at the heart of the M84 galaxy, something extraordinary defies this expectation. A pair of radio jets so perfectly symmetrical they could have been drawn with celestial rulers. These twin beams stretch over 12,000 light-years each, maintaining near-identical shapes and intensities across their entire length, a level of precision that shouldn't last more than a few centuries, let alone persist for millennia. What cosmic machinery keeps this system so impeccably balanced when every other supermassive black hole we've observed seems to revel in turbulence? The secret likely lies in M84's exceptionally stable accretion disk, the swirling platter of gas and dust that feeds the black hole. While most supermassive black holes dine erratically, gulping down matter in uneven clumps that warp their disks and distort their jets, M84's central engine appears to be fed by an unusually smooth cosmic conveyor belt. Millimeter-wave observations reveal a disk rotating with almost mechanical regularity, its inner edge barely wobbling as it funnels material toward the event horizon at a steady rate. This stability creates the ideal conditions for those textbook-perfect jets. When infalling matter enters the black hole's vicinity at a constant pace, the magnetic fields threading the disk can channel outgoing particles into coherent beams without the usual kinks or flares. But maintaining this equilibrium requires more than just an orderly meal plan. M84's black hole, weighing in at around 1.5 billion solar masses, seems to strike a rare balance between consumption and restraint. X-ray data shows it's neither starving nor overworked, hovering in a Goldilocks zone where the inflow of matter perfectly matches its ability to process energy. Too little gas and the jets would sputter out too much and the disk would become unstable, warping under its own heat and gravity. Somehow, this system has found the sweet spot where accretion becomes an art form. What truly sets M84 apart, though, is how its jets interact with their environment. Typically, radio jets plowing through intergalactic space get disrupted by clouds of gas or magnetic turbulence, their paths meandering like rivers encountering boulders. Yet these beams remain laser straight, suggesting the surrounding medium is far more uniform than expected, or that the jets possess some intrinsic stability mechanism we haven't yet identified. Some theorists speculate that helical magnetic fields coiled like springs along the jet's lengths might act as self-correcting guides, keeping the particle streams on course across cosmic distances. The implications ripple beyond this one galaxy. If we can understand how M84 maintains such precision, it could rewrite our models of black hole feedback, the process by which jets regulate star formation in their host galaxies. Most theories assume this feedback is chaotic, with outbursts clearing gas haphazardly. But M84 demonstrates that jets can also sculpt their surroundings with surgeon-like precision, potentially influencing galactic evolution in subtler, more controlled ways. For astronomers, this galaxy offers a masterclass in extremes, a rare glimpse of a supermassive black hole operating not at its messiest, but at its most refined. In a universe that usually favors chaos, M84's enduring symmetry stands as a quiet rebuke, proving that even the most voracious cosmic engines can sometimes achieve something astonishingly close to perfection. At first glance, the Virgo Supercluster appears as a bustling cosmic metropolis, its galaxies spread across space in what seems like a continuous tapestry. But when astronomers slice this expanse into precise distances using redshift, the stretching of light that reveals how fast galaxies are moving away from us, an eerie pattern emerges. In certain redshift ranges corresponding to specific depths within Virgo, galaxies vanish almost entirely, creating what scientists call a redshift desert. These aren't just minor gaps in distribution. They're vast regions where the cosmic census plummets dramatically, as if entire neighborhoods of the universe simply packed up and left. The mystery lies in determining whether these deserts are real structural voids or mere illusions caused by observational limitations. Early surveys suggested instrumentation might be to blame. Certain telescopes struggle to detect galaxies at particular redshifts due to atmospheric interference or wavelength coverage gaps. Yet as observations improved with instruments like the Sloan Digital Sky Survey, the desert stubbornly persisted. In some redshift slices, galaxy counts drop by over 80% compared to adjacent regions, a deficit too extreme to dismiss as technical error. It's like scanning a forest canopy and finding entire swaths where trees refuse to grow despite the soil appearing identical. One provocative explanation points to the supercluster's violent history. Computer simulations show that when galaxy clusters collide, their gravitational wakes can fling smaller galaxies outward at predictable velocities, creating redshift-dependent shells of ejected material with empty zones between them. Virgo's complex merger history, including its ongoing collision with the neighboring Fornax cluster, might have sculpted these voids through a series of ancient cosmic strikes. Supporting this, some deserts align with predicted splashback regions where galaxies would have been hurled outward after close encounters with the cluster's core. But alternative theories challenge this tidy narrative. The sheer scale of some deserts spanning hundreds of millions of light-years exceeds what cluster dynamics alone can explain. This has led to more radical proposals involving primordial conditions. During the universe's inflationary expansion, quantum fluctuations might have created subtle density variations that later evolved into vast bubble-like structures. If one such bubble overlaps with Virgo's redshift range, it could leave behind a fossilized imprint of emptiness, a relic of the universe's first trillionths of a second. The plot thickens when examining the galaxies that do survive in these deserts. Many show unusual traits, elevated star formation rates, peculiar metallicities, or oddly shaped stellar halos. These outliers might be tramp galaxies that wandered into the void from richer environments, or perhaps resilient systems that formed under rare conditions, allowing them to thrive where others couldn't. Some even appear to be aligned in faint, large-scale filaments crossing the desert cosmic tightropes where galaxies cling together against the emptiness. What makes these redshift deserts so transformative is their potential to rewrite our maps of cosmic structure. If they're real features, they imply the universe organizes matter on scales far grander than our current models predict. Surveys now actively hunt for matching patterns in other superclusters, probing whether Virgo's gaps are unique or part of a universal architectural code. Each new slice of redshift space peels back another layer, revealing that even in a seemingly crowded universe, absence can be just as telling as presence. The voids aren't empty, they're puzzles waiting to be decoded. Somewhere in the heart of the Virgo cluster, there's a cosmic contradiction brewing, an ocean of superheated gas that refuses to rage. This intracluster medium, a seething plasma hotter than the cores of stars, should be a textbook example of chaos. Simulations predict violent turbulence, with energy cascading through the gas like storm waves in an endless sea. Yet when astronomers peer into Virgo's core, they find something startlingly serene. Vast regions where the gas moves with unexpected smoothness, its ripples dampened as if an invisible hand has calmed the waters. The puzzle isn't just academic, it cuts to the heart of how galaxy clusters evolve. Turbulence plays a critical role in redistributing heat, accelerating particles, and even regulating star formation in member galaxies. Without it, clusters like Virgo should behave radically differently. So why is the actual cosmos defying our digital predictions? One camp argues we're missing microphysics, subtle interactions between particles that simulations simplify away. For instance, weak magnetic fields permeating the gas could act like cosmic shock absorbers, their tangled threads converting turbulent energy into orderly currents. There's even evidence that cosmic rays, high-energy particles zipping through the plasma, might play peacemaker, their pressure smoothing out eddies too fine for telescopes to resolve. But alternative explanations point to Virgo's tumultuous past. This cluster isn't a pristine system. It's a stitched-together patchwork of mergers, each collision sending shockwaves through the intracluster medium. Counterintuitively, these violent events might have left the gas more uniform, not less. Picture dropping dye into a stirred cup. Initial chaos eventually gives way to an even hue. Similarly, multiple merger shocks could have homogenized Virgo's plasma over billions of years, erasing small-scale turbulence while leaving behind a deceptively smooth facade. Supporting this, X-ray observations reveal faint, sloshing patterns in the gas, gigantic waves frozen in time, relics of past disturbances that once rocked the cluster. The controversy deepens when we examine where the gas behaves. Virgo's inner regions show the most pronounced smoothness, as expected in dense environments where frequent interactions might dissipate turbulence. But the outskirts tell a different story. There, the gas occasionally flickers with unexpected structure, filaments and cavities that hint at unresolved microturbulence. Some theorists propose this gradient reveals a hidden hierarchy of physics, large-scale mergers dominating the core's dynamics, while unseen forces like plasma instabilities or dark matter interactions govern the fringe. What makes this mystery so pivotal is its connection to one of astronomy's most persistent challenges, the cooling flow problem. Galaxy clusters should naturally radiate heat, allowing their cores to cool and form new stars. Yet they don't, and suppressed turbulence might explain why. Without sufficient stirring, heat could be trapped in the gas like steam in a lidded pot. If Virgo's smoothness is typical, it would mean our universe has built-in regulators mechanisms that quietly maintain equilibrium on scales we're only beginning to perceive. Every new observation peels back another layer. Polarized radio emissions hint at magnetic fields woven through the gas in complex geometries. High-resolution spectroscopy reveals slight temperature variations like whispers of long-forgotten disturbances. Even the cluster's resident galaxies might play a role, their motion stirring the plasma like spoons in soup, but in ways simulations struggle to replicate. The Virgo cluster isn't just defying expectations, it's offering a masterclass in how little we truly understand about the interplay between chaos and order in the cosmos. One thing's certain, this missing turbulence isn't just a glitch in our models. It's a clue, a signpost pointing toward physics operating in the shadows, shaping the universe in ways we've yet to fully imagine. Whether the answer lies in unseen forces, overlooked histories, or something entirely unexpected, the calm at Virgo's heart proves that even the most violent corners of the cosmos harbor secrets of stillness waiting to be uncovered. From the ghostly whispers of missing baryonic matter to the perfectly balanced jets of M84's black hole, our journey through the Virgo Supercluster has revealed just how much the universe thrives on mystery. These 25 cosmic enigmas, galaxies spinning in eerie unison, voids defying explanation, dark galaxies hiding in plain sight, aren't just curiosities. They're radical signposts, forcing us to rethink everything from the nature of dark matter to the very laws governing gravity. Every unexplained signal, every lopsided halo, every star-forming blob adrift in the void is a crack in the foundation of our cosmic understanding, hinting at physics we've yet to imagine. Think about what's at stake here. If filaments of dark matter truly funnel gas across millions of light years, they're not just scaffolding, they're the universe's circulatory system. If primordial magnetic fields synchronized galaxy spins, they've left a fossilized fingerprint from the dawn of time. And if the great attractor's pull can't be explained by visible matter alone, we might be staring at evidence of dimensions or forces beyond our current models. These aren't gaps in knowledge, they're doorways. Now imagine what's coming next. The James Webb Space Telescope peers deeper into Virgo's heart, hunting for the faintest dwarfs that could solve the missing satellite's problem. The Vera Rubin Observatory's relentless sky scans might catch blue blobs flickering to life in real time, revealing how stars form in the loneliest voids. Gravitational wave detectors could soon sense the final shuddering orbits of M60's binary black holes, testing relativity like never before. Each new instrument brings us closer to answers or to even bigger questions. So where do you stand on these mysteries? Do ultra-diffuse galaxies hide ancient cosmic laws in their dark matter halos? Is Virgo He21 a pure dark matter phantom, or just debris from a forgotten collision? Drop your wildest theories in the comments, because history shows the boldest ideas often start as speculation. After all, the Virgo Supercluster didn't become a treasure trove of secrets by playing by the rules. It's a reminder that the universe's greatest gift isn't just what we know, but how much remains gloriously, tantalizingly unknown. The next breakthrough isn't just coming, it's already hiding in plain sight, waiting for the right observer, the right moment to pull back the curtain. Stay curious, the cosmos is far from done surprising us.